Hi everyone, this video is for section 7.4, modeling changing amplitudes and midlines. In this particular problem that we're looking at, it reads, a spring is attached to the ceiling and pulled 19 centimeters down from equilibrium and released. After 4 seconds, the amplitude has decreased to 14 centimeters. The spring oscillates 13 times per second. Find a function that models the distance d. The end of the spring is below equilibrium in terms of seconds t since the spring was released. So again, with problems like these, I really do suggest that you maybe pause the video in this case and reread the problem. This is coming from number 12 from your textbook. So one of the first things that I want to note here is they're mentioning that the amplitude is changing. So this actually is pulling from what was covered in your textbook and in class called the dampened or the damped harmonic motion. So that means that our particular outcome or our particular function that we're going for is going to look something along the lines of f of t is equal to a times b raised to the t, and that exponent is just attached to the base b. It is not attached to the a. Recall that from Math 141, a represents your initial value in your exponential growths and decays. This is going to be followed by the sine of b times t plus k. Okay. And again, I'm noting that I'm going to be using the damped harmonic motion in this case because we're talking about pretty much how the amplitude is changing. So this is kind of acting as a key phrase here to give me some direction as to what kind of function setup I should be looking for. So to begin, let's just go through our regular checklist. So we do have our midline, which we've identified as k. They don't really indicate for you where this spring is set or how long the spring is, like your textbook does. All they mention is the word equilibrium, actually a couple of times. And equilibrium will just kind of say, let's assume it's just at your regular horizontal axis line. So since they're not giving me any specifics, I guess I get to, just say it's going to start at equilibrium or like spot 0, essentially. So from here, let's go ahead and do the amplitude. Which in this case, the amplitude is going to be represented by a times b raised to the t. So in order to uncover this one, we have to actually pull more information out. If you recall from Math 141, we were able to create the equation for an exponential growth or decay by using 2 coordinate points. So in this case, I know that at time 0, I know that the end of the spring is 19 centimeters away from equilibrium. And I also know that at time 4, so 4 seconds after release, the amplitude would be at 14. So in this case, we're watching, it kind of makes sense. If we let go of a spring initially, the end of the spring is going to be at its highest point because I've stretched it as far as I could. And then after that, it slowly but surely begins to pull back closer and closer to where it's being held. So my amplitude in this case is going to be decreasing. But in this case, what we can do is we can go ahead and say, all right, if I start off with y is equal to a times b raised to the t, I'm going to go ahead and drop in my first coordinate point to help me out here. So if I do that, I'm going to put 19 for my output, a times b raised to the 0. b to the 0 is just 1, so I automatically reveal that a is 19, and I can go back and use my second coordinate point. So this time I will say 14 is equal to, I know that a is now 19, b raised to the 4th power. Okay. So that being said, we can go ahead and divide both sides by 19, And this is, of course, not going to give me a very pretty number, but it's going to give me 0.7368, 421053, and that's equal to b to the fourth. So if you recall, we can raise both sides to a 1/4 power, or take the fourth root, depending on how you want to view that. And if we do that fraction raised to the 1/4 power, we're going to get 0.926, 496128. So we found b. So our amplitude in this case is going to be 19 times, and I'm going to round that to the fourth decimal place, so 9265 raised to the t. The next thing that we can do is we can find the period. And we know that in this case, the period is going to be we'll say p is equal to 1/13. And the reason being is because we're going to oscillate 13 times per second. So basically, what we're provided here in the narrative is the frequency. If I could spell. Frequency. Okay? So in order to find the period, remember that the period is time. So I'm basically, since I'm going to oscillate 13 times in 1 second, what I'm saying here is that it's going to take me 1/13 of a second to oscillate once. Okay. So then this allows me to find out what my horizontal stretch or compression is going to be. Again, b is going to be 2 pi over b, and that's going to give me 2 pi over 1/13. And again, we can use a shortcut here to help us out. Or what we could also do, I'll stick with the longer hand version. So what I'm saying is we can do 2 pi divided by 1/13. So I'm going to take it out of that division bar and use the operation. That is going to be 2 pi times the reciprocal. So my b is going to be 26 pi. So now we actually have everything that we need to put our final solution together. Okay, so we'll start off with our f of t, and that's going to be equal to our 19 times 0.9265 to the t power times the sine of 26 pi t plus, in this case, we said that our midline was 0, so we really don't need to include that last piece there. But here is our function that's modeling the change in amplitude as the spring continues to kind of bounce after being released over time. I hope that this explanation was helpful. If you do have any other questions, please let me know.